This is a vertical curve example. We have a sag vertical curve with equal tangents, and moving from left to right, this curve joins a negative 1.2% grade to a positive 0.8% grade. As shown, the PVI of the vertical curve is at station 75 plus 00, and the elevation of the PVI is 150.00 feet. And this is a classic vertical curve problem with what we call a control point. Sometimes the control point is a cross street. Here it's a pipe, and we need to ensure that there's sufficient cover above the pipe between the finished roadway elevation and the top of the pipe. So the pipe is located at station 75 plus 40, and the top of the pipe elevation is at 152 feet above sea level. And the requirement here is that the center line of the finished roadway must be 3 feet above the pipe. So the first thing that I always like to do is to choose one side of the vertical curve to proceed from. You can solve this problem from either the left or the right. In this example, I'm solving it from the left. So I simply extend the entering tangent to the pipe, that's the green line, and then I draw a triangle. It's the orange triangle here. So I connect the point at the bottom where the green line sits right underneath the pipe. I draw a vertical line through the center of the pipe. I then draw a horizontal line connecting the finished roadway elevation over to the PVC, and then I connect with the hypotenuse those 2 points. So we know that the elevation of the final roadway needs to be 152, which is the top of pipe elevation, plus the 3 feet of cover here, or the finished curve elevation is 155 plus 00. And I can also find the elevation of this point down here, since we know that this point has to be 155. Since we know the elevation of the PVI is 150, and we know that the distance between the center of the vertical curve and the center of the pipe is 40 feet, because we were given this stationing, 75 plus 40, that's a distance of 40 feet. So we can calculate the elevation of this point here, which is 150, the elevation of the PVI, minus 40 feet times the slope, which is minus 0.012. So we know the elevation of this point down here, which is 149.52. We also know the elevation of this point, which is 155. Same with this point over here. So we've pretty much fully described the triangle. So we can add a couple more labels. We know that the height of the orange triangle is 155 minus 149.52, or 5.48 feet. So what we're going to do is look at the horizontal length of the triangle. We know that in any vertical curve, it has equal tangents. So what we're trying to do here is find the length of the vertical curve that will satisfy the requirements of this problem. So the distance from the PVC to the PVI we call L over 2, equal tangent vertical curve. We know this distance is 40, so we can describe this side of the triangle. X is L over 2 plus 40. And to complete the problem, all we need to do is find the station and elevations of the PVC now that we have L. So we simply take the elevation of the PVI and we just go up and to the left and up and to the right, a distance of L over 2 at the appropriate slope. So we find that the PVC elevation is 162.17, PVT elevation is 158.12. And then the stationing is just going to be 75 plus 00 minus 1/2 L, 2029 divided by 2. So the stationing of the PVC is 64.85, and the stationing of the PVT is 85 plus 14.5. So that's a great classic example of a vertical curve, a sag vertical curve with control point. So what we want to do is solve for L. And so for this triangle, we have the length of two sides in terms of L. You remember that the difference in grades, A, is the absolute value of G2 minus G1, In this case, G2 is plus 0.8, G1 is negative 1.2, so 0.8 minus a negative 1.2 equals 2. And then we have the basic equation for any offset at a vertical curve at any location, and the equation for that is ax squared over 200L. Here we know that x is measured from the left-hand side, L over 2 plus 40, so we're measuring from here to here. And we know that the offset, because we calculated it before, is 5.48 feet. So in this equation, we just plug in our version of x. So then we have a nice equation, 5.48 feet, only in terms of L. It's a quadratic equation that we can easily solve. So L over 2 plus 40 is x. So A is 2x squared divided by 200L. We can clean up this equation and simplify it. So the result of that cleanup is L squared minus 2032L plus 6,400 equals 0. You might remember the quadratic equation. We can solve for L, and we just simply plug in the values of A, B, and C. Negative b plus or minus the square root of b squared minus 4ac over 2a. So, of course, we get two solutions. One of them is 2029 and one of them is 3.15. The 3.15 value is infeasible because the vertical curve would be too short. It would be way down here. So what we have found here is that L is 2029. We could round that to 2030, but for the calculations here, I just kept that value of 2029. And